Hello there everybody. Today I'll be talking to you about Argand diagrams. Now Argand diagrams originated from the theories of Argand, who was a mathematician. His full name was Jean-Robert Argand. He was born in 1768 and his work on complex numbers was quite revolutionary. And he's got quite an interesting story, which I'd recommend you looking up if you're interested. So an Argand diagram is a way of drawing complex numbers on a set of axes. So as I said in one of the previous videos for my complex number series, for complex numbers we have weird axes. We have the imaginary, which would usually be the y, and we have the real, which would be on the x. And if we have the equation z equals a plus bi, a would be plotted on the real, so this would be a, and bi would be on the imaginary, so that would be b, and then we'd have a straight line, and that is a plus bi, and we can find out the angle here, we can find out the length of that line, and we do lots of cool stuff with that. But for this video, I'm going to be discussing how we can draw Argand diagrams, and I think it's quite simple. So the first diagram we're going to be looking at is a simple one. We're going to be looking at 2 plus I. So we look at 2. We know that 2 is the same as A, and I is the same as B, and I, there's only the coefficient in front of I is a 1. So we have 1 and 2. So we have 2 on the x on the real, and on the imaginary we have 1. So 2 and 1, and then what happens is we draw that line, and that is called a half line. Let me just do one more example in case you haven't understood the concept yet. It's an easy concept, it's just some weird notation. So let's look at 15 plus 3i. So we go back to the axes, 15, 3, bam, that was easy. So now we move on to where it gets more complicated. So now we look at here's a question, I'm just going to discuss it and break it down. Modulus of z minus 3 plus 4i equals 5. Now this may throw you off, and I'm going to teach you how to solve this, and there's quite a cool graph that comes out of it. So because it's modulus, we should probably square both sides, as if you square a modulus you get a positive, because modulus if you square it you get a positive, so we'll square it in a bit, but not just yet. So if we have z like we have here, just remember the equation, z equals x plus I y, where x is real and y is also real, but because it's in front of I, it shows up on the imaginary axes. So if we have z equals x plus iy, assuming that x and y are given values, that's what it would look like, but that's not what we want right now. So let's substitute in x plus iy. So x plus iy minus 3 plus 4i, and this is all being modulus, gives us 5. I'm not sure if modulus is a verb you can describe that as doing something, but if it's not, I just made it up just now. Okay, so x plus iy minus 3 plus 4i equals 5. Now let's group the like terms. Let's put x minus 3 together and iy plus 4i together, as you want the i's to be together. Modulus of that equals 5. Now, here's where it gets fancy. We can factorize out the i's on this side. So iy plus 4, x minus 3 plus equals 5. And since I equals root minus 1, if we square it, it becomes minus 1. So x minus 3, we're squaring the whole equation by the way, minus y plus 4 squared equals 25. Now you probably just realized this is the same. This is the equation of a circle. And if you don't know the equation of a circle, it's x minus a squared equals, I'll show you, x minus a squared plus b, what was it? Y minus b squared equals radius squared, where a is the where AB is the center of the circle. So we have a circle here, center 3 minus 4. So let's draw this. And 25 equals radius squared, and square root of 25 is 5. So now we have let's draw this up. Imaginary and real. And we know the center is 3. Okay. I can't remember what I was saying. Oh yeah, the circle. So we know that the center of the circle is going to be 3 minus 4, and there's going to be a radius of 5. So 3 minus 4, it's going to be around here. Oh no, it's wrong around. 3 is right, but obviously minus 4, so it's going to be down here somewhere. And then because it's a circle, we can know it's got radius 5. But actually, this is quite a difficult question because we know that this radius, it's 5. And if we do Pythagoras' theorem, we can imagine 3, 4, 5 is a 3, 4, 5 triangle. So now we know the radius must go through the center, must go through the origin. So the radius reaches the origin. So we know this circle will look something like this. And that's a terrible drawing. Let me just rub out some of this stuff. Okay. Just go to the circle. Okay. Take 2. So we know 7 minus 3 plus 4i equals 5, and this is being modulus, gives us this. And we know that this is 3, this is minus 4. This is just a sketch. It's not like an accurate diagram, but the modulus, the Argan diagram would look roughly like this. And there you have it. That's how you draw an Argan diagram. But obviously there are other types of Argan diagrams, and I will go into that right now. So that was one equation. This is another equation that we're going to do. We're going to put z on both sides now, because before we had z equals something. Now we're going to do z equals z minus 6. Okay. Now this is where it gets, you could argue it's slightly tricky, but it's just a simple method to it, and we'll explain that now. So, just give me a second. Okay, so we draw back our axes, and we know that z minus 6, let's say, equals 0. We're going to split this up into 2 equations, y equals modulus z, and y equals modulus z minus 6. So z minus 6, let's say that equals 0. Z minus 6 equals 0, that means z equals 6. So z equals 6. And y equals modulus z on the left. So we know that we want y equals 0. And there we have it. Because we're just imagining, but we're drawing 2 lines, y equals z minus 6, which would look like that, and y equals z, which looks like that. But because it's modulus, I love using that verb. If you don't know how modulus works, when you have y equals modulus x, you reflect the x in the x-axis, so it always remains positive. So we have something that looks like this, and yeah, we can see that we have halfway between, and this equals 3. So it's where these 2 lines cross, and they both cross at 3. And you can prove that algebraically, but I'm just going to explain it just for this video. And there you have it. It's a cool, so that's explaining it. It's a cool graph, but just to show how the graph actually looks like, it's going to look like x equals 3. There. So modulus z equals z minus 6, and that's 3. There you have it. It's very simple. Okay, now we're going to assume, now we're going to put a complex number in there, make things a bit more exciting. So now we have the following. Z minus 3 equals z minus I, modulus both sides. Now you're wondering, oh, what do we do? I'm going to explain what we do. We draw the axes. Y equals z minus 3, so we know it goes through 3. Z minus I, but because it's a complex number, and this is the imaginary real axis, we plot the 1 on the real, and then we have x. And now what we want to do is we want to find the perpendicular bisector of these two lines. Now you can figure that algebraically using y equals mx plus c, but let's just assume that's what it looks like. So there you have it. We have three types of Argand diagrams. We have the circle, we have what we just drew, which is a half line, I believe, and we have the vertical line. So those are the three types of Argand diagrams. I hope you enjoyed this video, and I hope you learned something. I'm going to do some more complex number videos, and I hope you enjoy them. And let me know if there are any other complex number topics you want me to talk about. And I hope you enjoyed. So have a great day, and remember, maths is the way.